Just want to reiterate that's a we won an award. That was supply chain operations, not me on my own. There was a team involved, and technical authority were also there. But, so let's go through some sleeper stuff. Many of you have seen this topic before. In supply chain operations, we're looking at improving sleeper designs, reducing sleeper costs, so the affordability comes in part of this. But at the same time, let's try and make the sleeper perform better. In terms of climate resilience, improving lateral stability, lateral resistance is part of what we're doing. I'm going to take you through our new concrete sleeper development, the lateral resistance testing we've been doing with Southampton, and since then a few other collaborators have come into the mix as well. Controlling track buckling, so some of the things we do, not well, but we try and apply, whether it's pre-works or post-works, to control track buckling and improve lateral resistance. CRT adjustments, what sort of adjustments we can make to, and as Nick said, CRT does mean money in places, so trying to enhance that CRT value to give us more headroom for, before the speed restriction needs to be applied. And a bit on LERPs, USPs, and a bit on gluing as well. So step back into the classroom a little bit. What does a sleeper do? As a system, its main function is there really to support the rail support and load transfer into the ballast. If you were to look at the functional requirements of what a sleeper should do, maintaining gauge, rail plane, inclination, lateral resistance as part of it. There's a few other things we've started to use sleepers for as well. So one of them is cables. We attach cables to sleepers. And also, one thing that is missing from there is we also have to support a conductor rail pot on the end of a sleeper to support conductor rail. So that's another function that we should be considering for sleepers when we design sleepers. So working with the University of Southampton, this sort of goes back to 2023 when we started to present some of these graphs, and a warning, you're going to see a lot of wiggly graphs. I won't expect you to be able to read them or understand them, so I'll try and briefly summarize them with a few tags for you. Using that data, we thought, why can't we improve the EG47 concrete sleeper, the shallow sleeper, and the G44, the standard sleeper that we use, and try and get better performance out of it to give it some future proofing for predicted rail temperature increases. This is a test that we did in 23. We again publicised this and discussed this. This is where we started to understand where steel sleepers, concrete sleepers, EG47s, the shallower type, G44s, we did a testing on under sleeper pads to see how much lateral resistance how much we gain from under sleeper pads on sleepers as well. We also looked at LERPs, and LERPs is the anchor thing that we stick onto at the end of a sleeper or in the middle of the sleeper to basically put a spade into the ballast to stop it from moving. Expensive to install, also a bit cumbersome, and so we're trying to sort of a cost saving to try and reduce using those. What we did find was the EG47 concrete sleeper, as we know and love, is actually a really low lateral restraint. It's just above timber and just above composite sleepers as well, down that lower range, when the G44 is 50% more, and that's mainly down to depth, not just weight, but depth. And then this is where we also found about the under sleeper pad, so it doubles the lateral restraint. It is similar to adding a lateral end resistance plate. So by adding or specifying an under sleeper pad with the sleeper, not just for ballast protection and for other improvements that it gains, but it does also gain that additional lateral resistance. It's not just us that's done this testing. Other suppliers have done the testing. Other laboratories have done this testing. Europe is now doing a lot of this as well and starting to realise, actually, should we add this to the spec for under sleeper pads? Because it's actually a game changer in terms of lateral resistance. So this is the EG47, collaborated with Cemex, Trackwork Mole. We basically gave them carte blanche to play around with the designs to reduce, put slopes in, reduce the weight, put in more vertical faces, so we've got more ballast locking. The slopes will promote more ballast pressure on top by weighing down onto the sleeper as well. And actually, we started to get to something like some of the old sleepers used to be. We used to have a lot of trapezoidal, a lot of sloping sleepers and so on. Whereas I think when we started going to the G44, we went very boxy and rectangular, and it lost that sort of shape, that profile that was there for a reason. So maybe we're going back to where we used to be with this. But by doing that testing and looking at the baseline, we've now seen that actually, yeah, we can improve this. So fundamental thing about the EG47 is we're not changing the footprint, we're not changing the strand pattern, we're not changing the main mold itself. We're keeping all that the same, so it reduces in cost and change in manufacturer. We're just changing the concrete profile surrounding all of those bits that hang off it. Results were 48%, 49% increase in lateral resistance for the new shape. So it's massively improved it, way beyond the G44 now. Similar to a G44, just below a G44 with a USP, but it just goes to show by changing the shape, we've got somewhere really positive. In terms of the volume change, we've got a reduction in volume as well. I think it's 5%. So with reduction in concrete volume is reduction in cost, so we can save in that as well. So there's a saving for us, and that will come back to our customers who purchase our sleepers as well. So with a USP, we didn't see a huge difference. So we're seeing that the USP did give it that additional benefit, but not as much as the benefit by changing the profile of the sleeper itself. So these are some of the tests. Again, just flicking through because it's a lot of wiggly lines that I would not expect you to understand. We had 5 different concepts of EG47s that we're trying to see what shape works best. Large pockets out, small pockets out, castellated and so on. Some ends different as well. The C5 worked the best. That gave us that sort of 50% improvement. The benefit of the undersleeper pad was still a benefit in terms of the early unhooking 3mm loss of geometry where you start to move a sleeper before it then drags further on. So that unhooking is quite an important thing to look at. So it still does provide that in terms of maintaining geometry and so on. Bit of a warning here, this testing isn't the be-all and end-all. It's a simulation that we can repeat, and we can do it with all our sleepers and all our suppliers. It's similar to what is being done in Europe with a single sleeper test. Also working in conjunction with British Steel. They're doing a similar test using similar different methods for pushing steel sleepers and so on. And also working with other suppliers to look at this. So it's a similar method. It's one that's specified similar to EN. But it's not a dynamic test, it's a static test. But the ballast has been compacted. G44, improvements there, again, keeping the shape, keeping no changes in the strand patterns, but changing the shapes. We did the same tests with Southampton, and we got a 7.5% increase. So not great, but it gives us more headroom. That's 5 degrees, 6 degrees, 7 degrees, so it still gives us some more headroom for the future. The big thing there was the 7.7, the 8% saving in the volume, which will go into cost of concrete, which will, again, could save 5, 6, 7, who knows what for pounds for a sleeper. So there is a cost that we can put into that. All of these were then tabulated, so we've got all of our results, all the different sleepers we've pushed. We've pushed other undersleeper pad suppliers just to see how they compare. Do we need to make sure the specification for undersleeper pads includes lateral resistance? LERPs on EG47s, we never tested those before. We tested a LERP on a G44, but not on EG47, so we did that testing as well. And we also tested a track-work mile sleeper, a CEMEX sleeper, and we looked at the two. Next steps really are to combine those designs so that both suppliers can make them using their current manufacturing, carousel method, long line method, and not changing any strand patterns, but making sure we can do it. So we need to do the testing, the dynamic testing, and so forth to prove that the concept works. So what other features? The sleep obviously plays this part, but the features that we look for in controlling and preventing track buckling, and some of the things that we've learned from the testing. So it's the depth of the sleeper, the width, the base of the sleeper as well, because EG47 is slightly wider, but almost 60% the depth of a G44. Adjoining sleeper, so you can see the Y-frame sleeper that's used on some tram systems, it's used on some light rail systems, but by joining that together on very tight curves, and we're talking 15-meter curves on some mountain railways, that's why it's used. So it doesn't. So Y-frame sleepers have got that additional lateral resistance. The bottom photograph is the H-frame sleeper, the heavy-duty sleeper. So again, connecting those together, that's where you start to get a rigid track form system. You've got torsional stiffness in clips, so the Voslo clip there, providing additional torsional resistance via rail seat width, twisting, and making the ladder effect more rigid, so you don't get a more snaky effect in the track. So the torsion resistance of clips, again, is really important in sleeper design. And then there's increasing the friction, the contact surface, which all that under sleeper pads does as well, increasing all of the other surfaces for contact with ballast. But what measures do we have to control it once it's in the ground? We put sleepers in the ground, we've got old track, we've got existing legacy track. We know we've got issues trying to reduce the CRT, or not reduce the CRT, but reduce the likelihood of buckling. We use LERPs, that adds around 4 degrees. Shoulder gluing, I did a search on ballast gluing, and that little picture there came up with a little tub of ballast glue, but I wouldn't use that on ballast. I think that's more for railway modelers, but just goes to show there's no awareness of, or anything that shows you what ballast gluing does when you do that search. So wider shoulders, we know wider shoulders do offer some amount of lateral resistance. Is it big? We don't know, question mark. Spraying rail white, tests have shown 3 degrees, we can get out of that, maybe 5, but keeping it clean and maintaining it, being white every time. We used to do it a lot on S&C, and some areas still do it. It's not, you know, it's not sacrosanct, but it's something that could be considered. And I remember Easton, we did a trial, it was Mark Paget, did a trial of water cooling, got it down to 5 degrees, so reduced it down to 5 degrees, so upping the CRT by 5 degrees. It only lasted for 2 hours, but you know, so there are things there doing water cooling. The reverse of what Nick's trying to do with raising the temperature for stressing. So then if we take a lot of this findings and we look at how we can actually update and modify our table 6 in mod 14 for CRT values, we can then start to say, actually, yeah, with this track form, with that undersleeper pad, with that sleeper, and with all of these other bolt-ons, we can get a CRT that's, you know, very high, and will we ever get to that CRT in the future? So it's worth looking at that. We're not there yet, but presenting that information, presenting the testing as part of the 2102 group with Eric, and also with Brian Whitney and the CRT group as well. That's the sort of things we're looking at so that we can sort of promote that. This is some work that British Steel have done, just to prove that actually steel sleepers are very good at lateral resistance. 3-4 times, I think I may have flagged up on here. This is a 3 sleeper test, so British Steel have done the single sleeper test and a 3 sleeper test, so pushing 1 sleeper but with 2 either side of it. And they've shown there that we get around 3 times of a G44, and I think compared to LERPs as well, you're still, you know, massively above. So there is that twisting effect we do get with a weight on it, as a weight to resist that. Then you don't get as much, but you do get that tipping effect. However, the restraint for those is a lot higher than we imagined, so sort of questions some of the restrictions we've got on steel sleepers in terms of curvature and CRT. And this is the single sleeper push test as well. Similar results, just showing that it's 3 times that of LERPs. We've pushed on to working with other collaborators, so Vossloh are aware of the work that we were doing. They reached out to us and said, oh, by the way, we're doing this Vossloh Maya tool, looking at modeling CRT and having sort of predictive outcomes. It has 35 different inputs in terms of the characteristics you do. Even ballast type is in there. There's 3 different types of ballast type that you can put in there that have different outcomes in terms of CRT and buckling management. So we're hoping to, in 3 weeks' time, set up a small working group. It's not a community of practice, it's more a little technical group of discussing various different models from Europe, different products we have, some of the testing we've done, and with British Steel as well, to look collaboratively how we can improve this. And also do all our tests, do the same thing. Are we coming out with the same outcomes? And how do we get that through to everyone to say, look at these improvements, let's try and introduce these. Again, load more squiggly lines. And this one is for ballast. So we did with Southampton, and this is going to continue on, I think, with Southern, with Ross and with Column, to do some more sensitivity analysis on ballast profiles, ballast heaping, reducing it down. But ballast does give you 22%, so if the correct height, so it does give you quite a lot there. But reducing it down, and it's more about the mass rather than the the steep slope, and the slope beyond it is very important as well. So the slope that goes beyond the shoulder is very important. So more work needs to be done on that, and Southern are looking at doing that to get some cost savings as well from dropping from shoulders. Working with Goldschmidt, so this is glue ballast. They approached Southampton. We were keen to see what effect gluing has on sleepers, on the lateral resistance of sleepers and track. We'd been using gluing to stabilize shoulders and to create that beam effect along the edge, but we didn't know how effective it was. We still don't know how long it will last, 5 years, 10 years, 15 years. We need to understand that. But the results here showed that, again, 3 times more than LERPs itself. So we're way up there with glue ballast. And I'll go into some of the cost savings as well. We hadn't previously done this test, so we had to understand what glue does offer in that space. We also looked at the undersleeper pad underneath to see, did the glue penetrate underneath and ruin the pad? And the answer was no. It didn't go just slightly to the edge, but the USP was still doing what it was supposed to do. So it's still happening there. Yes, you've got a glued shoulder to the side of it, where the end of the sleeper corner is supporting into it, but it didn't affect the USP and the ballast side of that as well. So one of the comparisons we did a little cost saving on Popart's Junction, which was on Southern, that Ross did some work on for us, and David as well. Looking at, this wasn't particularly for glued, but I did one on glue. We looked at the savings by using undersleeper pads instead of LERPs, and this was the savings for you using glue instead of LERPs, so gluing the shoulder. And you can see there the saving is around 30, so we're talking about the cost for gluing is around 11,000, the cost for LERPs is around 45,000. So you've got a 34,000 pound saving there. And that's just on 100 meters of track that we do. And you can do it in one shift. So you're not talking about lots of people installing over countless amounts of shifts. So that's led to us looking at also the savings for LERPs. We've done this before with, I think, Brian and myself and a few others, where we noticed that we were spending a lot of money on LERPs and installing them. And I think Weston's spent over $1 million a couple of years back on LERPs. And it does increase the unit rate. The unit rate goes up, up to around £695 a metre. The unit rate goes up by using LERPs. And that's not in our unit rate. We don't account for this. We just find out when we've got curves that are 400 metres or 300 metres, or we see on the design and go, we may need LERPs here. So it's one thing to consider. And this is the statement of why not use undersleeper pads? They have the same lateral resistance. Yes, there could be a void there, but there is an allowance for void in the CRT value. If you get track voiding, you deduct a certain amount. So we know that is the case. But by putting the USP on from the start and installing it from the get-go, then we get that improvement straight away. And we don't need to keep adjusting it when we need to go in and tamp. Every time we need to tamp, we have to bring up the anchors and put them down again as well. Then they get left off, and then people tend to say, okay, we're not going to use them anymore. So at least this is a permanent fix. And for Battersea Park, I think the figure was actually more than that. Sorry, for Popart's was more than 40,000 saving, something around 80,000. We're being very pessimistic with that. But I think, Ross, you've got the actual figures. But again, a huge saving. And in terms of cost per metre and unit rate saving, then the 695 is quite staggering. So what have we found from this? A bit of myth busting. We found that the EG47 does provide a better design and is as good as the G44. Not all USPs have the same lateral stability and stiffness. Having too many recesses sometimes doesn't allow the ballast to sit in the pockets. It doesn't allow it to interlock. So reducing that amount we found works best, and that's that design there showing that as well. The shoulder ballast bonding, showing that we can get 2 to 3 times that of LERPs. And gluing undersleeper pads on the underside of composite sleepers, FFU bearers, or side-cut sleepers, or any composite lightweight material can give you a similar lateral resistance to concrete sleepers and concrete as well. And there you go, that's the end of my talk. Thank you very much.